Hey guys, Mrs. Stanton here. Real quickly, let's talk about topic 11, student activity sheet 5. Okay, so what we're doing here is we are talking about the asymptotes and wholes of rational functions. Okay, just a reminder here, our parent function is y equals 1 over x. And if you remember correctly, we said that x could not equal 0, as a 0 in the denominator would make that an error, undefined. And we also said that y could not equal 0 because there was no value for x that would get us a 0 over here. Okay, and when we had that graph, it looked something like this, where both sides got infinitely close to those lines of x equals 0 and the line of y equals 0, but they never touched it or crossed it. Okay, and those are what we called asymptotes. So let's talk about how we find our asymptotes. The first thing I want to talk about is our transformation function. I'm just going to call that TF for short here. Okay, transformation function. And if you guys remember correctly, we've been dealing with these transformations all year. You should have y equals a divided by x minus h plus k. All right, so let's see how this h and k values affect these asymptotes here. It's really quite simple. You're going to have a vertical asymptote, okay, VA, at this line right here. Well, what affects this line? Well, when the graph shifts left and right, which is my h value, okay, we're going to have a vertical asymptote at the value x equals h. And remember, they go in as opposites. If we see a negative here, it's positive here. If we see a positive here, it's going to be negative here. Okay. We're also going to have a horizontal asymptote. You guys can use HA for short. At the line y equals, what affects the horizontal? Well, when the graph shifts up or down, what letter does that? K. All right. Then taking a look at this real quick, just because it's really easy to see here, we're going to say that domain, in order to find our domain, well, if we look at this graph up here, our domain, our x values go from negative infinity into that vertical asymptote, and then it picks up again to positive infinity. So we're going to say that my domain is going to be negative infinity to the h value. We're going to use, say, u to show and then we're going to go from that h value to positive infinity. Whereas our range is going to go from negative infinity to that k value and from k to positive infinity. Okay. Now, transformation form's great. We can see how the graph is shifting up or down, makes it really easy on us. However, there's things that transformation form cannot tell us that quotient form can. Okay, so let's, again, just to keep things nice short here, we're going to talk about QF, quotient form. Okay. An example of this, guys, that's like if I had, as an example, like x minus 3 over x plus 4. Okay. I could have my big old x squared plus 4x plus 3 over something that said x squared minus 2x minus 3. Okay. So those are examples of our quotient form. Now let's take a look at how we find some of this information. Remember when we saw problems like this, maybe there was some directions. This is from like the first activity sheet. We said to simplify these. So the first thing that I want you guys to do, always, always, always on this, is going to be to factor the top and the bottom. Okay, that's going to be the biggest thing. Factor the top and bottom first before we do anything. Okay, so let me tell you some information that we can find once we factor that. Okay, the first thing we're going to find are the x-intercepts. Okay, our x-intercepts. What are those? Those are going to be the zeros of the numerator. Okay. The next thing that we're going to talk about is the y-intercepts. Okay. How do I find the y-intercepts? We're going to plug in 0 for all the x values and simplify. Okay. Pretty basic so far, right? Okay. The next thing I want to talk about are what we call discontinuities, or holes. Okay. When you see a hole in the ground, just as an example here, if I'm walking along, if this is my path, if there's a hole right here and I'm right here and I'm going, oh, hey, we're going to walk this way, and I see this hole, I'm not going to walk through it and plunge to my death. I don't know where that thing's going. No. Okay. I'm going to kind of jump over it and then keep going on my merry way. Okay. So when we see a hole, that's something that it cannot equal. Now, why can it not equal it? Well, remember how we factored the top and factored the bottom? Well, this is where we cross off what's in common. Our discontinuity, our holes, are the values that cancel out, that can be simplified. Okay. So again, those are the common factors that we simplified between the numerator and the denominator. Okay. And you'll see that in example here. And again, they're there, but they're not because they simplified. Again, I'll do an example here in a minute. The next thing, let's talk about that vertical asymptote. Okay, this one's the easy one. Where am I going to find that vertical asymptote? Okay, I'm going to find that vertical asymptote at the zeros of the denominator. Okay, the zeros of the denominator. If you go back on some of our homework, you know how like it told you to simplify and then state the excluded values? Well, this is those excluded values. Okay. Now, the last that I want to talk about are going to be, I'm going to change up my color here. I'm not sure why. I just feel like changing up. Okay. The last thing I want to talk about are going to be our horizontal asymptotes. Now, these get there's rules involved here. Okay. And we're going to look at the degrees. When I say look at the degrees, I mean that I'm going to look at the degree here. So here my degrees are 1, here my degrees are 2. We're going to look at the degrees. Okay. At the degrees. And what we need to know about that, we have 3 different cases. Okay. So what you need to know, when my degree of the numerator is greater than the degree of the denominator. So say I've got like an x squared over an x. Okay. When my degree of the numerator is greater than the denominator, I have a horizontal asymptote at y equals 0. When they are the same, when the degree of the numerator equals the degree of the denominator, that's like an x over an x, okay? We're going to divide the leading coefficients, okay? And then lastly, when the degree of the numerator is less than the degree of the denominator, that's like if we had an x over an x squared. What we're going to do is we're just going to state that there is no horizontal asymptote. So let's real quick do an example here. Okay. We're going to give the example of f of x equals x squared plus 4x minus 12 all over x squared plus 8x minus 20. Okay, so I told you guys step 1, not an option here, factor. Okay, my numerator, this is going to factor into an x plus 6, x minus 2. And in the denominator, when I factor that, I get x plus 10, x minus 2. Okay, so first thing I see right away, guys, these x minus 2's. Okay, those can be simplified. That's our common factor that cancels. That is our hole. We are going to have a hole at the value of x equals positive 2. Okay. See, it's there, it's in the problem, but it doesn't exist because we canceled it. That's where we hit that hole in the ground. Okay. Now, the next thing I want to talk about, okay, let's talk about that vertical asymptote. Okay. If you look back on our notes, we said that we have a vertical asymptote at these zeros in the denominator. Okay. Well, where do I have the vertical asymptote here? At negative 10. X equals negative 10. Okay. Let's look at my horizontal asymptote. Okay. Look at my degrees. My degrees are equal. If you want to put a note there, equal degrees. Well, what did we say when the degrees are equal to each other? We said divide my leading coefficients. Okay. In this case, my leading coefficients are 1. That would just be 1 over 1. So I have a horizontal asymptote at y equals 1. Okay. Next, I want to look at my x-intercepts. Okay. My x-intercept is going to be my zeros of the numerator. So I have an x-intercept at the value of negative 6. Okay. I don't like it when students write it like that. Because it's an intercept, you need to write it as a point. The x-intercept is when y equals 0, so it's negative 6, 0. Okay, same with the y-intercept. Again, guys, write it as a point when x is 0. So we're going to plug in 0 for all of those. You could do it here or you could do it here. In this problem, we would say negative 12 over negative 20. Again, zeros, that all cancels, and I'm left with this last set here. That can reduce. We can divide each of those by 4, and we end up with a positive 3 over 5. So my y-intercept is at 0, 3 over 5. Okay. If we're talking domain and range here, guys, it may help to graph this a little bit. Okay. We know that there is a vertical asymptote at negative 10. We're going to call that negative 10 over there. We know that there is a horizontal asymptote at 1. And we also know that whenever this graph gets to the value of 2, there's going to be a hole over here. Okay. This function is positive. So just quickly graphing this, I'm going to put it in red so you can see. Does that, and it's going to do that. So if that helps you guys, we can look at domain and range. When I look at my domain, now this is where things get a little spicy. Okay. The first part's easy. We go from negative infinity to what was that asymptote? Negative 10. We then go from negative 10, be careful here, we stop it at that hole. Well, we said the hole was 2, and then we're going to pick it up from 2 to positive infinity. My range, okay, my range, we're going up from negative infinity to that first asymptote, which we're going to say is 1. And then, in this case, guys, normally we would include that hole, whatever that y value is when x is 2. What do we get for y? Nothing there. So you can have your teacher explain why we're not going to do that. I'll explain more of that to my students in class, but we're going to just go ahead and continue this from 1 to positive infinity. Okay. And then your teacher will let you know what practice they want you to do. Have a good night. Good luck studying. Bye.